Shit. This roll of filament costs $300 for 500 grams. To put that into perspective, a regular roll of filament costs between 20 and $30 for a kilo. So this is more than 20 times as expensive, but what makes this so special? PEEK, or polyether ether ketone, is regarded as one of the highest performing engineering thermoplastics in the world. It has excellent mechanical strength, temperature resistance and chemical resistance. It has a tensile strength of 105 megapascals, which is around twice the amount of the materials that we used to print with. And it has a temperature resistance of 250 degrees. At that temperature you bake pizzas. So how cool would it be if you can 3D print with this stuff? And no, this is not done on a typical consumer desktop 3D printer. Ever since I heard about this material, I wanted to print with it. But PEEK is typically printed on industrial machines with specialized heaters, and those costs between $10,000 and $100,000. I bet that I can do it on my Bambu Lab X1C. The X1C is known for being a beginner-friendly plug-and-play 3D printer. It's like the Apple of 3D printers. It's polished, closed, and not to be tinkered with. And that's exactly why I'm using this printer for this project. It's just so wrong that it's perfect. In order to print PEEK, we need heat, and lots of it. The print temperature is around 400 degrees Celsius, so therefore I have this hotend from DyzeDesign who sent it to me that gets up to 500 degrees Celsius. Both DyzeDesign and 3D4Makers made their appearance on this channel when I built that water-cooled printer for printing those rims, and I love collaborating with them. We cannot mount this hotend to a stock X1C and call it good. Fortunately, this is not a stock X1C. I replaced the mainboard and extruder earlier this year, and it runs on RepRap now. We have full control over this machine, and our only limit is the hardware, and we will be pushing those limits. I got this heater from Big Tree Tech, the Panda Breath. This is a pre-production version that they gave me on Formnext after I told them about this project. And they also supplied me with custom firmware that gets rid of some maximum values, and the only thing that we have to do is just circumvent some safety measures. The first thing that would probably melt are these carbon rods, and to be really honest with you, my initial idea was just to crank up this temperature and see these things melt, but the purpose of this video is not to just blatantly melt down this printer. I want to print PEEK with it, and with this knowledge I think it makes more sense to replace those rods with the steel ones. Also because I know that some people have issues with these rods, so maybe it's just interesting to see if you can swap them out with these steel ones. This will make the gantry heavier, but we aren't aiming for speed. We are aiming for survival. We have a bit of a challenge. This whole gantry is a replacement part because these rods are glued in here. And I think that our best option here is to reverse engineer this ourselves, to 3D print these end blocks. So we can easily mount the rods in them ourselves. Not only that, we can improve on it, and we have the option to use whatever sliding mechanism we want because we have the design files then. So let's start reverse engineering. I was pretty happy when Onshape reached out to me for sponsoring this project because I made the switch to Linux a while back. I didn't really have a professional CAD program that ran well on it, and Onshape runs in the browser, so it's platform independent. I was even able to run it on an old Mac while being on the road. Because it's online, every action is automatically saved and you can restore your project to any point in time. It's even possible to branch your design and merge it later on, just like Git. It works very similar to the CAD systems I was already familiar with, and once you get a hang of how the data structure works, it becomes really convenient to use. So I reverse engineered this gantry and I had to come up with a solution for mounting the rods and the pulleys. And this is the design I came up with. It's printed out of polycarbonate with carbon fiber on the Prusa Core 1L. I use this material because it's really stiff and temperature resistant enough for what we are going to use it for. I also bought standard 10mm steel rods that I cut to length earlier. The pulleys are screwed in place using set screws, and the rods are held in place with this clamping system. I designed the whole gantry and it should basically be a drop-in replacement. Professional CAD users or companies evaluating Onshape can receive up to 6 months of Onshape Pro at no cost. Check out Onshape by using the link in the description. And now we have to find a way to get these bushings off of here. Alright, that was incredibly stupid. Carbon fibers everywhere, and if you want to fuck up your lungs, then this is a very effective way of doing it. Please just use a hacksaw, do it outside with lots of ventilation, and preferably have some mask. The fitment was a bit tight and I had to hammer the rods in. After some encouragement, they fitted perfectly. I could just use the original bushings and they seemed to slide really well. After hammering the other block on it, I used a glass plate to make sure that everything was parallel and not twisted. The gantry sprung back to the center, which implied that it was a bit too long. So I had to give it a good whack and now it was running as it should. I placed back the belts in a proper Core XY configuration and I think that this result looks pretty good. I just flashed the custom firmware that I got directly from ByQ. This enables it to reach higher temperatures than it's used to. So what I'm doing, it's not made for reaching that, but it's physically capable of reaching pretty high temperatures. Usually you connect this thing to your printer and sync it and control it from the printer. But this is running RepRap firmware, and it's just much easier to control this directly through a web interface. So they're both in the same network, and now I can just power it on. And it powers on and it works. There is hot air coming off of it. The only thing I have to do is circumvent this trip, the safety feature that will trip when the temperature reaches above 70 degrees, I think. So let's get rid of that, so it will go as high as physically possible. And then I can place it into the printer and start putting the printer back together. It goes without saying that what I show in this video, don't do it yourself unless you actually know what you're doing. Not that I exactly know what I'm doing. Yesterday I circumvented the safety features of the Panda breath It was a pretty easy procedure, not to be replicated of course. And I placed the pendant breadth inside of this printer. But before placing back the panels, I'm going to insulate them. I'll do that with ceramic felt. I've used this stuff before for the printer that printed the rims and also for the grill plate printer. It's easy to work with, it can cope with extremely high temperatures, and the plan is to just glue them directly to these plates. And I also have more than enough to insulate more stuff in this printer. So we will both protect some stuff in there and also keep the warmth inside. I used some acetone to remove the remains of the double-sided tape and found a very smart way to determine the size of the ceramic felt. I applied some painter's tape on the inside of the panel, cut it to the right length and measured it. Ceramic felt damages easily, so it must be handled with care. This makes it easy to cut it to the right size though. I applied some glue to the inside of the panel and I just hope that this can cope with the temperatures. Well, it is on the cold side of the felt, so it should be fine. In the meantime, I started the print that I designed earlier that has an incorporated bristle by using alternating bridges. Once the print was finished, I was able to cut these bridges in half, which results in this bristle. The idea is that the wires of the heated bed will move through this bristle and that the warmth of the chamber is captured better. It honestly doesn't fit perfectly and it wasn't an easy part to design, but it seems to do the trick. I also applied glue on the backside and added more ceramic felt to it. I made a slit at the location where the purge chute used to be, through which I routed the power cable of the chamber heater. Lastly, I placed the side panels back and it took me way too long to find out why something was off. Because of the ceramic felt, the fitment was really tight, but I eventually managed to mount the side panels to it. I glued in all the ceramic felt and I managed to put this thing together. I had to use some longer screws at some points because it was a pretty tight fit. And it's really looking like a furnace now, which is a good thing. Also, here on the back, the ceramic felt goes in front of the motors. So they are a bit insulated from the rest of the chamber. And if those motors overheat, I can have a bit of airflow here at the back, which is insulated from the inside of the chamber. So the last thing that we have to do now is add this DyzeDesign hotend to it. In my first video about this mod, I already made a bracket that fits an orbiter extruder. And I modified it in such a way that it also fits a DyzeDesign hotend now. This bracket was made by PCBWay. They sponsored that video. And they are also sponsoring this video because they made the modified bracket now out of the same technique because it fitted so well. And I just wanted to have the same quality. I just got the package from them. So let's see what they sent. So as many already know, and it's in the name, PCBWay, they make PCBs, but they also do 3D printing and also injection molding, sheet metal fabrication. And what I like about the 3D printing service is that they supply parts that are made out of the jet fusion technology. And those parts look really good. They're really strong. What I also like is that I can add inserts to it. I supplied them with a drawing pointing out where the inserts needed to be placed. And well, they are in there. So if you're interested in professionally made 3D printed parts or sheet metal or PCBs, then check out our website, PCBWay.com, or visit the link in the description. Well, first let's see if this fits in here. Oh wow. This is a sick package. So I removed the extruder bracket that I made earlier and replaced that with our new bracket. Because the first bracket I made fitted perfectly, I was pretty confident that this would just fit as well. And now my Bambu Lab printer has a hotend that goes up to 500 degrees. We have to do a little configuration. The Dyzend Pro has a different temperature sensor. 2000 degrees. This is the moment where the problems really started. I quickly found out that this is not just a matter of the right configuration, as this hotend uses a different temperature sensor. For a moment I thought that it would be better to replace the big 3-tech board with the duet board that I used for my grill plate printer, but started to realize that this will open up a whole new can of worms. So I decided to modify the firmware in such a way that I can use the SPI bus of the display output so we can use a temperature sensor module. Compiling on Linux made me feel like a true hacker man, but also comes with every single compile error you can think of. I spent days trying to figure this out, much longer than I would like to admit, to be honest. Regular viewers of the channel know that things tend to escalate a bit here. Well, I moved to Prague. The idea for this video was to finish it in the Netherlands, but trying to get the temperature sensor to work took so much time that I was unable to finish it there. I had to postpone it. I had to move all the stuff here to this new studio. And yeah, well, here we are. I found out that the temperature sensor is just a regular thermistor, but with a much higher resistance. So it's read out as open circuit. But it was a hardware problem. I couldn't get the SPI to work, but because it's a normal thermistor, in theory you should be able to use the standard circuit. But I had to modify that circuit. And a positive thing about living in Prague is that we have everything now here. I can just take the tram and go wherever I want to go to. Watching out of the window makes me realize that this is my life now. I went to an electronics store to buy resistors to influence the circuit of the temperature sensor input. Then I went to a place called Bambu Lab, where they help and promote the repair culture in Prague. They let me use the soldering equipment for this tricky modification. After I replaced that thermistor, it worked for lower temperatures, but after I did a PID tune, the temperature started to collapse around 300 degrees. But in reality, the temperature rose much further to the point that the whole block turned blue. This was due to the thermistor getting into a much lower resistance, so the steps were simply too small. As a last resort, I connected the thermistor to an unmodified input and just added a 100k resistor in parallel, so it wouldn't show up as an open circuit at lower temperatures. And after lots of tuning, I finally got it somewhat accurate between 250 and 450 degrees Celsius. Shall we just start and print peak on that thing? nothing beats the delicious smell of freshly baked peak. I loaded up the filament and the leftover patchy was getting smoky at 420. The print started well, but I quickly noticed that the probe was not retracting anymore, so I had to help it a bit. I noticed another problem. The fan duct of the bracket started melting and pieces of jet fusion nylon were getting embedded into the print. Yes, it was soft, and in hindsight it should have been printed out of metal. Oh well, I'm not using that fan anyway, so I removed the bracket and modified it a bit. I also had the idea of using a silicone sock to protect the probe a bit, and I used a ton of Kapton tape to hold everything together. Well, that probe was gone. It melted, so I had to manually move the bed against the nozzle and ignore Z-homing altogether. Also, the display had shown its last image and was also gone. To top it off, the nozzle got clogged and I got severe under extrusion. I was unable to unclog it, so I replaced it with a bigger 0.6mm nozzle. Technically I printed peak, but am I happy with this result? Well, no. I want to get more out of this. I want to print something bigger, something that I'm actually going to use. I'm gonna print a coaster based on the coasters I already designed and use regularly. This will be a pot coaster that can withstand the heat of a hot pan. I ran into a slight issue though. The bed adhesion was good, but it lifted the plate from the magnetic bed. I was thinking on how to solve this issue, and the next day I printed clamps out of polycarbonate that will hold down the plate. I needed to crank up the temperature further and took some precautions. I set the chamber temperature to 90 degrees and the bed temperature to 140. It briefly reached that and then it dropped. My assumption was that there is a thermal fuse somewhere in there and that I had to dig it out in order to reach these temperatures. Removing the magnetic cover was a lot of fun to do, which makes for a nice afternoon activity. Eventually I got it off and there it was, the thermal fuse. I heated it up while measuring its resistance to double check its functionality and it tripped. What I'm doing now is not safe and I don't recommend you to replicate this. This blob of tin is the thermal fuse now. I used some sticker remover to get rid of the remains of the bed and luckily I got a wham bam plate left that was sent to me a while back. Thanks Peter, you just saved this project. It was a bit too small, but it does the trick. I started the print and manually adjusted the bed height while it was printing. To everyone who criticized me in my last Bambu Lab video that it didn't make sense to modify it, I'm the one printing peak on it right now. This is what you get when you have full control over the equipment you own and not have it locked down. This is the world I want to live in and I continue to fight for it. Also, I'm happy that my new house didn't burn down with all the nice wooden furniture in it.